So, hello students and welcome to this module in the lesson about district heating, district cooling and electricity production. This is the last module of the lesson, and what I will do is that I will describe the task I want you to do for a past degree, for a past grade that is. To be able to do that task, you will have to know basically everything from the previous modules in this lesson. If you feel that you don't, or you feel insecure about parts, then try the self-questions, the self-test questions that are available here. The self-test that you find here contains all the questions from the previous modules, and there is a time limit. So doing that test may give you an indication of if you are well prepared to do your full examination task or not. What I want you to do is basically a feasibility study for an area that you select yourself. And I want you to write a short but high quality report on that. Remember that this is a master level class in an engineering subject. So your report shall be academic master level quality. There are two main possibilities now. One is that you are taking this lesson all by yourself. In that case, will no one scrutinize your report, but I still think you should write a report just for practice, if nothing else. The other chance is that you are doing this in the realm of a university. In that case, you will have instructions to follow, and they will tell you what you shall do and how it will be assessed. So, what I will do now is to show you the technique to do such a superficial feasibility study. And we will limit the study to only look at district heating. As you see from this slide, the task contains finding local data. And I cannot help you on that. You know what the aim is, what you need the data for. And you will be the one to know your local authorities, statistics offices, etc. Ultimately, what you have to do is to find data to set up a duration diagram that is reasonably trustworthy for the area you have selected. And now I want to remind you again, your study shall finally be presented in the form of a short report. And that report shall be of a good academic quality, considering this is a master level course. So the data you use must be from serious and trustworthy sources. And if you suspect the data to be biased or insecure, you must try to compensate for these insecurities and write down good motivations in the report. The background given in Module 2 should be enough for you to estimate a reasonable duration diagram, provided you can find the proper base data. You will need the duration diagram to find the first value for the anticipated peak load. And to that peak load, you will have to add a certain amount of heat losses. If your selected district is in a very densely populated city area, you may assume that the heat loss is below 10%. But then, if you have selected an area with single-family houses that are quite far apart, you may end up with losses maybe 30 or even 35%. So, again, make a guess, but you simply have to have a starting point. What you want to do now is to make yourself a schematic map showing the peak load distribution. So put a transparent paper over the real physical geographical map of the area and split the district into sub-districts. Try to make these sub-districts somewhat alike when it comes to the peak load, and try to make them with a simple geometry and each reasonably coherent with respect to the type of buildings and customers in them. You may, for example, try to fit the office buildings into one sub-district, and the multi-story apartment houses into one sub-district, and the university campus into one, and so on. So maybe the whole thing looks something like this once you're done. What you want to do now is to get yourself a first picture of the main distribution piping. So what you want to do at this stage is to look in the handbook you downloaded in Module 5. And you want to look at section 4.4, starting at page 71. Depending on how your schematic map looks, you will see that you may end up with a situation where a star structure is the natural, or maybe a line structure, or maybe something else. In the example shown in the slide, it seems like a star network is the most logical. So what you do is to outline approximately how you want to distribute the heat. For the moment, you do not care about the real geography as it comes to the piping. Straight lines are fine at this stage. In the previous module, I mentioned that you should really plan for severe fractures. So what you would do at this stage would really be to plan for double feedings to the different areas, so as to be able to shut off a fractured pipe and instead feed the area in another way. I do not demand that you actually do that in this task, but I want to remind you that supply security is one major part of the planning considerations. You will notice that I have filled in the fine mesh distribution in area number 4 only. And in area number 3 I have only indicated. But there would be similar grids in the other ones too. I'll come back to this. Now add up the peak loads. And then do an assumption for the forward and return temperatures at peak load. Even if you assume a very efficient system, you will have to appreciate that the lowest return temperatures will only be obtained at low load. And at peak load will the return temperature, generally speaking, become higher. So if your dream is a 35 degrees return temperature, you should plan for the peak load case to have maybe 10 or maybe even 15 degrees higher return temperature. And then you have to select a forward temperature for the peak load case. When you do that, you have to consider two things. In the third module was the connection between the district heating water temperature and the COP of the lithium bromide water absorption heat pump outlined. The higher the temperature, the higher the COP. On page 61 in the District Heating System Handbook will you find figure 4.4. In that figure will you find a qualitative reasoning about the temperature level and some other factors. So your choice of forward temperature must be motivated in the report. And the motivation may be different if you think that a district cooling system might be a good idea in the long run or not. So now you have to think forward. Will you later want to include also district cooling? In this slide, I've also set up the equation to use, including the dimensions, from which you can compute the necessary volume flow in each of the main pipes. Use 1000 for the density. You do not have to be more accurate than that. And use 4.18 times 10 to the third for the CP value. In Module 5, did I mention approximate velocities that you want to have in the different pipes? So you will use the equation in this slide and reasonable velocities from Module 5 to compute pipe diameters. As you see in this slide, have I indicated 3 different pipes. They are indicated by the different thicknesses. So limit yourself to 3 diameters, not to overdo things. Let's now call the pipes primary for the biggest ones. In this example, would the primary pipe transport 197 megawatt? It ends in area 3, where the main hub is. The secondary pipes would be for, say, 50 megawatts plus minus. So there will be 3 secondary pipes. 54 megawatt to area 1, 36 megawatts to area 2, and 62 megawatts to area 4. They will end in local hubs, from which the tertiary pipes extend. The tertiary pipes will extend along the roads, each maybe 1 megawatt or so, depending on how the situation is. Finally, will there be the local pipes, those that actually connect the customer to the tertiary pipes. In area 3, as you see from the slide, do I suggest that the tertiary pipes are connected directly to the main hub. Now look in the handbook, page 72, section 443, and you will see that what I am actually suggesting is that you stick to standard routing. And I want you not to have too many types of pipes in the system. So what you want to do with a schematic map is to draw yourself an overall system structure and to find the main diameters of the pipes to distribute the total load. Find the diameters, not the lengths. Now you could compute the pressure drops in the different pipes. So you could draw yourself the pressure length diagrams. But doing that is actually beyond the current task. So now look at page 64 in the handbook, and you will see some examples of pipe diameters. But remember that within this task, you are not limited to existing tubes. The important thing is that what you shall prove is that you understand and that you can do the calculations and the thinking. You shall not prove that you can find values in specific tables. But there is one set of tables you have to look at. And that's the ones in section 13.4, starting on page 183 in the handbook. Because in these tables will you find values for the thermal insulation data, and you will need that later. By now you will have to bring up the real geographical map of the area. Because what you shall do now is first to figure out the total length of each pipe category. What you want to do then is to have the pipes follow the streets. So you need to have a street map, and you must have decided where you want to have hubs and substations. And then you need to find the lengths. Since you are doing this as an examination and not as a consultant, a certain amount of simplification and shortcuts are okay. Try to do the primary and secondary categories of pipes accurately. But for the tertiary, maybe you can assume that they would group-wise have the same length and then just count the number of streets or do something similar so as to simplify things. Again, the aim with this task is for you to show your understanding, your skill and your competence. It is not to make you do relatively simple things over and over again. When you have done the calculations for primary, secondary and tertiary pipes, you also have to do the local piping. Looking at figure 414 in the handbook, page 72, one may assume that the tertiary pipe is connected by local pipes to the houses on both sides of the street. So then is the length of the individual local pipe the distance between the houses on both sides of the street. So Use that as a measure and count the houses. It will give you a fully realistic value, and that is what we are after. By now you have collected quite some data, and now it's time to do a bit of calculations. So let's have a look at some simple equations. What you want to do now is first to compute the mean outer diameter for the pipes in the system. Now you have to remember that you will most likely have two types of piping. The primary and the secondary will most likely be so big that they are single pipe. Look in table 13.1 on page 183 in the handbook. That table shows a set of single tube pre-insulated steel tubes. On the next page is another table, and that is for twin tubes. When you compute the total length for single tubes, you must remember that there is one forward tube and one return. So if the physical distance for the primary tube is 2 kilometers on the map, then will the length of the primary tube become 4 kilometers. But the local pipes, those connecting the individual buildings, are most likely small enough to be dual or twin tubes, and in that case is the total length on the map equal to the total length of the piping. As for the tertiary pipes, they might perhaps be small enough to be dual or maybe not. It does not matter if the inner diameters you have computed fit exactly to the inner diameters in these tables. Round your values off to values in the tables if you want to, or do a simple approximate interpolation or whatever. The important thing is that by the aid of these tables you shall get two values for each one of your 4 categories of pipes. These values are the outer diameter and the specific heat loss. And then compute mean values for these according to what is shown in the slide. I just want to point out one thing. With the approximate equations that I will suggest you use, you do actually not need the mean diameter. But there are other equations to use to do the same calculations, and for those, at least some of them, you would need the diameter. So you might as well calculate the mean diameter. It's not such a big thing. But now comes a slightly more complicated calculation, and it involves a bit of guesswork. What you need to do now is to characterize roughly the operating conditions for the system on a full year basis. And you will do that by the degree time number, which is expressed in degree seconds. The times will come from the duration diagram, and they will represent high load, medium load, and low load. Anyway, that's how you will treat it now. If you had access to real data from an existing system, you would do it much more accurately, actually summing up momentary data. But you do not have anything like that. And then, once you have the times, then you need to have the mean temperatures for the 3 load cases. The calculation itself is simple enough. Now you have all you need to estimate the losses in the grid. The estimate you do now is much more solid than the guess you did in the initial phase of this task. So now you should compare your values and consider how much off your initial guess was as compared to what you have estimated now. And ask yourself if there is a good reason to recalculate things from that stage or not. The final value for your feasibility study is the line load. That is the value you are really after. But then, of course, in your report, you will naturally discuss the total losses in the system and other factors. So, good luck.